Welcome to the fourth lecture of module 3. In this module, we are discussing analysis of the batch reactor kinetic data. In the last 3 lectures, we have mostly covered the analysis of the batch reactor data by integral method of analysis, and the volume of the reactor we have considered constant volume. Let us have a brief recap of our last lecture we had. In the last lecture, we discussed homogeneous catalyzed reactions, then we have discussed autocatalytic reactions. So, for the homogeneous catalyzed reactions, we have seen that we need to have some catalyst which will give the product or enhance the rate of the chemical reactions, but at the same time the reactants itself can convert to the products without any catalyst. So, the reactions proceeds in two pathways. So, this is called parallel reactions, conversion of a certain component through non-catalytic and catalytic reactions, and that we have discussed under homogeneous catalyzed reactions. In autocatalytic reactions, that means one of the product is reacting with the reactants to produce products. So, this is called autocatalytic reactions, and to start the autocatalytic reactions, some of the product must be present at the beginning to start the reaction. Then we have discussed irreversible reaction in series reaction, then first order reversible reaction and second order reversible reaction. And we have concluded that any reactions more than second order is very difficult to treat analytically. So, in this lecture we will consider constant volume batch reactor data analysis, and that is differential method of analysis. Then we will consider varying volume batch reactor, and that also we will analyze by differential method of analysis as well as the integral method of analysis. So, under integral method of analysis we will mostly consider zero order, first order, second order and nth order reactions. So, let us start with constant volume batch reactor with differential method of analysis. As we said at the beginning, in case of the differential method of analysis, we directly take the differential form of the rate equations and test it whether it fitted the desired data obtained from the batch reactor. The methods of the fitting generally follows 3 steps. In step 1, we plot the concentration of a component versus time t. So, if we plot concentration versus time and we start with a concentration say Ca naught, and we calculate the concentration at different time. So, if we plot the concentration versus time data which we have given over here, then carefully draw a smooth curve to represent the data. So, with the eye as a guide, we can plot the data smooth curve joining the points, and as you can see, the data, all data may not pass through all the points. So, this is how we will follow step 1, and then in step 2 determine the slope of this curve at suitably selected concentration values. Then the slopes which is dCA dt is equal to RA are the rates at this composition. So, we have to select at different locations points, and we have to draw tangent to calculate the slope and so on. Now, next step would be we need to search for the rate expression which would represent the rate versus concentration data. That can be done. So, our search would be search for the rate expression which would represent RA versus concentration. So, this can be done two ways. One, we can pick a particular rate form, pick a particular rate form, that means minus RA is a function of concentration into K. So, K into function of concentration, K is the rate coefficient, and we can plot like this as we have done for integral method of analysis. Similarly, here we will take the minus RA is equal to minus dCA dt versus we considered a guessed kinetics which is function of concentration, say first order, second order, third order, whatever may be the kinetics we can consider here, and we can plot the data and if it is fitted with a straight line passing through the origin, then the guessed kinetics is fine. So, if the data fitted by a straight line then the guessed kinetics rate form is the correct one. Now, second way of testing the rate form, let us consider nth order form. Consider nth order rate form, say that is minus R A is equal to k into C A to the power n, and we can take logarithmic of this one, then we can write minus log of minus R A, which is equal to log of minus d C A dt is equal to log k plus n into log C. So, now if we plot log minus R A or log minus d C A dt versus say log C A, so then we can get the data which is fitted with a straight line, but in this case it will not pass through the origin. So, there will be intercept and the intercept is log k. So, this intercept is log k and slope of this will give is the order of the reaction n. So, from slope we can calculate order of the reaction and then we can calculate the rate form. So, let us take an example, the same example which we have considered for the batch reactor data analysis by integral method. If we consider the same example from the Levenspiel, consider a reactant A decomposes in a batch reactor as per the following reactions A2 products, and the variation of the concentration of A at various time in the reactor is measured and given in the following table. So, this is the table where column 1 represents the time and this is the concentration. Now, we need to find a rate equation using differential method of analysis to represent the data. Okay. So, if we plot the data concentration versus time, we will get the concentration time data as we have seen. So, first we have to plot the concentration and time data and we have to draw a smooth curve by hand, which is shown over here. Now, we have to select different concentration as we have given time and concentration, these are the concentration, and for each point we can calculate the tangent if they fall under the smooth curve. So, as we can see all these data point fall under the smooth curve. So, we can calculate the tangent at different locations, say we can write column 3 Here for each concentration we can calculate from here the dCA dt, that is the tangent. So, for the first case it would be 10 minus 0, that is the concentration difference, divided by 0 minus 75. So, it would be about minus 0.1333. Similarly, for this case it would be 10 minus 0 divided by minus 3 minus 94. So, it would be about minus 0.1031, so on. So, we can calculate all these data points and we will get, for 1 it will be 3 minus 1 divided by minus 10 minus 300. So, it would be about minus 0.0065. So, the other data points we can write is minus 0.0658, then minus 0.0410, minus 0.0238 and minus 0.0108 and 0.0065. So, these are the dCA dTA values. From this concentration versus time plot we can draw different tangent and we can calculate different dCA dt. So, now we need to guess kinetics, say nth order kinetics minus R A is equal to minus dCA dt, which is equal to k into Ca to the power n, and we need to take log, as we have taking logarithm of both sides. So, then we can write this is ln minus R A would be equal to ln minus dCA dt would be equal to ln k plus n into ln Ca. So, as we have said, this is y, this is intercept, this is slope and this is x. So, this is now if we plot the data, so this is 0 and concentration is say 0.2, say 0.4, 0.6, 0.8, say 1.0. So, this is ln Ca values and the ln minus dCA dt as we have calculated earlier, we can plot them. So, this is minus 2.2. So, this is say 0.2, this is 1.8, this is 1.6, this is 2.0, and this is say 1.4 minus 1.4, this is minus 1.2, this is minus 1.0, and this is 0.8. So, now if we plot the data, we can see that the data would be fitted like this. So, it will give the intercept here is about ln k is about minus 2.305, and we would obtain k from here. K is equal to 0.005, and the slope from here we will get n is equal to about 1.43. So, if we use this data, we can write the kinetic rate form, which is minus R A would be equal to minus dCA dt, which is equal to k into k is 0.005 liter to the power 0.43 divided by mole to the power 0.43 into second. This is k into Ca to the power 1.43, and the unit is mole per liter second. So, this is how we can obtain the rate equation or kinetic form of the particular reactions using the differential method of analysis. Now, one warning for this case: to use the differential form, as we have said, the data should be fitted with a guide with the eye. That means, if the data are like this, and if we plot with the guide with the eye, we could have drawn the data which would connect this with a smooth curve. But if we the same data, if we plot with a computer with polynomial fitting, say our data is like this, so our data is like this, and we want to fit a 5-degree or 6-degree polynomial. The polynomial may fit the data like this, like this. So, it will take all the data points. So, this could lead to disasters for the analysis of the differential form of the rate equations. That is why, for analysis of the differential form of the rate equation, we must have the most accurate data which we can, by which we can draw a smooth line, and in general the kinetic data are sometimes scattered. So, we need to draw the smooth line with a guide with our eyes instead of drawing with different degrees of polynomials in a computer program. Now, let us consider varying volume batch reactor and how to analyze them by differential method as well as integral method of analysis. The varying volume reactor are most conveniently used in case of the microprocessing field. Suppose if we consider a very small reactor like this, so you can consider a bead kept over here in a tube, and then as soon as the reaction proceeds the bead will move from. So, this is movable bead, and this is the reactor. The initial volume is V naught, and V is the volume at any time t. So, this is an example of variable volume systems, and in general what we do, we operate this reactor at constant pressure and isothermal conditions. That means, as soon as the reaction volume changes, we move the bead, keep the total pressure of the reactors same. In general, we keep to operate this reactor isothermally. So, if we consider volume and conversion relations is linear, we can write for this case V at any time volume would be related to V naught into 1 plus epsilon A into x a, or from here we can write x a is equal to V minus V naught divided by V naught into epsilon A. Now, if we differentiate this, we can get dxa is equal to dV divided by V naught into epsilon A. So, here epsilon A is the fractional change in volume, fractional change in volume. So, this fractional change in volume happens between no conversion and complete conversion, between no conversion and complete conversion. So, as per the definition, we can write epsilon A would be equal to V when x a is equal to 1 minus V when x a not equal to, that is equal to 0, complete conversion, So, V x A is equal to 0 is, that is no conversion, and V x A is equal to 1 is complete conversion, divided by V x A equal to 0. So, this is by definition epsilon A is the fractional change in volume between no conversion and complete conversion. Now, let us take a reactions and see how to calculate epsilon. So, now we will find out the fractional change in volume. Say, consider a isothermal gas phase reaction. A to 4R. Now, if we start the reactant A, start with pure A. So, then our epsilon A would be, as per the stoichiometry, 1 mole of A produce 4 mole of R. So, it would be 4 minus 1 divided by 1 is equal to 3. So, epsilon A would be 3. Now, in the second case, if we start with 50% inert with 2 volumes of reactant mixture, yield on complete conversion 5 volume of product. So, that means if we take 2 volumes of A, it will produce, as per the stoichiometry, 8 volumes of R, but we had 50% inert. So, we had 1 volume to 4 volume products. So, total 5 volumes, and then we had 50% inert with it. So, epsilon A would be equal to 5 minus 2 divided by 2, which is equal to 1.5. So, from here we can see that the epsilon, it depends or it takes into accounts both stoichiometry as well as the presence of inert. So, now we will see the relations between the concentration and the conversion. So, concentration versus conversion relationship for varying volume batch reactor. So, we know that Na is the moles at any time would be related to Na naught, that is the initial moles, into 1 minus Xa. This is we have seen from the stoichiometry. Now, we can write Ca is equal to Na by V. Now, in this case, this V is related with the fractional change in volume. So, we can write Na is Na naught into 1 minus Xa divided by V is V naught into 1 plus epsilon A Xa. So, this we can write Ca naught into 1 minus Xa divided by 1 plus epsilon A Xa. So, if we just rearrange this, we can write Ca by Ca naught would be equal to 1 minus x a divided by 1 plus epsilon a x a, or if we rearrange this, it would be x a is equal to 1 minus C a by C a naught divided by 1 plus epsilon a C a by C a naught. So, this is the relations between the concentration and conversion for isothermal varying volume or constant density system. This is for isothermal varying volume or constant density systems. Now, the rate equations for varying volume batch reactors, we can write minus R A is equal to minus 1 by V into d N A dt. Now, if we substitute V and Na, so then these relations will come in terms of the conversion. So, this would be minus R A would be equal to C A naught by 1 plus epsilon A x A into d x A dt. This can be obtained as we know V is equal to V naught into 1 plus epsilon A x A and Na is equal to Na naught into 1 minus x A. So, we can calculate dNA is equal to minus Na naught dxa. So, if we substitute these two over here, so then we will get minus Ra is equal to 1 by V naught into 1 plus epsilon A x A into Na naught into dx. So, Na naught by V naught is Ca naught. So, Ca naught by 1 plus epsilon A into dxa dt. So, from here we can write this. Now, in terms of the volume, we can write this equations minus R A would be equal to C A naught by V into epsilon A into dV by dt, which is equal to C A naught by epsilon A into d ln V divided by dt. So, this is in terms of the volume. Now, if we consider differential method of analysis for the varying volume batch systems, the procedure for the analysis of the varying volume batch reactor data using the differential method of analysis would be similar as we have done for the constant volume systems. In this case, the dCA dt, this term would be replaced with either Ca naught by V into epsilon A dV dt, or Ca naught by epsilon A d ln V dt. So, all other method of analysis are same, like minus R A is equal to minus dCA dt. So, in this case the dCA dt for the varying volume systems we have to substitute with this term or with this term. So, then the method of analysis as we have done just before, it would be similar. So, this means that we need to plot ln V versus time. And then calculate the slope. Now, let us consider the integral method of analysis. First, let us consider 0 order homogeneous batch reactor data for first order system, and since it is for 0 order system, since it is 0 order, so it is independent of the concentration. So, the red equation should be minus R A is equal to Ca naught by epsilon A d ln V by dt would be equal to K. Now, if we just integrate, so we will have Ca naught by epsilon A ln V by V naught would be equal to Kt. So, this is the integral form of the 0 order reactions. Now, if we plot ln V by V naught versus time, so we would obtain a straight line passing through the origin with a slope is equal to K epsilon A by Ca naught. This is when epsilon A is greater than 0. When it is less than 0, so the curve will lie in the opposite direction. So, it would be like this, and slope would be same K into epsilon A by Ca naught, and this is only for epsilon A less than 0. So, in this way we can test the 0 order reactions by integral method of analysis for the varying volume systems. Now, let us consider the first order reactions. So, for first order reactions, let us consider unimolecular type of reactions, and as we have considered in case of the constant volume systems, it would be similar. It would be minus R A is equal to Ca naught by epsilon A d ln V divided by dt is equal to K into Ca. This is first order. So, we can write the Ca, we know the relationship Ca versus conversion. So, K into Ca naught into 1 minus X A divided by 1 plus epsilon A X A. Now, if we replace X A by V and then integrate, from the earlier equations which we have derived the relations between X A and V, if we substitute that over here and then integrate. So, we would obtain minus ln 1 minus delta V divided by epsilon A into V naught is equal to k T. So, here delta V is V minus V naught. So, now if we plot minus ln 1 minus del V by epsilon A V naught versus time. So, the data would be fitted with a straight line passing through the origin, and from the slope we would obtain values of k. So, if it passes through origin with a fitting with straight line, then it is follows the first order kinetics. So, this way we can solve the first order reactions for the varying volume systems. Now, if we consider the second order reactions, let us consider bimolecular type of second order reactions, say twice A2 products, or we can consider A plus B2 products with Ca naught is equal to Cv naught. Then we can write minus Ra is equal to Ca naught by epsilon A d ln V dt is equal to K Ca square. Now, if we substitute this concentration terms like earlier, it would be K Ca naught square into 1 minus X A divided by 1 plus epsilon A X A square. Now, similar way like first order, replacing X A by V relation, we would obtain after the integration with algebraic manipulations, we will get 1 plus epsilon A divided by V naught into epsilon A minus delta V, this into delta V plus epsilon A ln 1 minus delta V by V naught into epsilon A is equal to K Ca naught T. So, now if we plot either, so this part versus time, it would fit the data passing through the origin. So, is a straight line passing through the origin with a slope k into Ca naught is the slope. So, this way we can solve the second order reactions by integral method of analysis from the varying volume batch reactor data. So, now if we take nth order reactions, it is similar to the constant volume systems. We consider nth order kinetics and then feed the data by the integral method. As you can see, it is not the straightforward as in the case of the constant volume systems. So, in general, except zero order, first order, second order, systems, other reactions are not treated by integral method of analysis. Since the higher order reactions are a bit complicated and in general it is not treated using this integral method of analysis. Now, let us take some problem to see the how to use those method which we have discussed for constant volume as well as the varying volume systems. Say first order reversible liquid phase reactions, A2R and concentration Ca naught is given 0.05 mole per liter, Cr naught is equal to 0 and which is taking place in a batch reactor, and after 8 minutes conversion of A is 33.3%, while equilibrium conversion is 66.7%. We need to find the rate equation for these reactions. So, solution for this we can do. We have reversible reactions A to R. Let us consider the forward reaction rate is K1 and the reverse reaction rate is K2. It is given that Ca naught is equal to 0.05 mole per liter and Cr naught is equal to 0. That means, no product is present at the beginning. Equilibrium conversion is given, that is XAE is equal to 0.667, that is 66.7% conversion. Now, if we take assume the constant volume batch reactor, that is our assumption. Now, as it is happening in the liquid phase, so we can consider constant volume batch reactor, and then the second order kinetics as we have derived earlier, we can write the integral form of the equations ln minus ln 1 minus xa by xae is equal to K1 plus K2 into T. Now, if we replace the values which are given from here, K1 and K2, from these relations we can obtain the relations between K1 and K2. So, if we substitute the values, it is minus ln 1 minus, we can see after 8 minutes. So, t is equal to 8 minute, the conversion is 33.3%, that is 1/3. So, X A is equal to 1/3 and X A E is 66.7% is 2/3. So, if we substitute these values over here, this is 1/3 divided by 2/3 is equal to K1 plus K2 into time is 8 minute. So, from here we will get K1 plus K2 would be equal to ln 2 divided by 8, which is equal to 0.086625 minute inverse. So, this is a relation of K1 plus K2, say this is equation 1. Now, from the thermodynamics we know that the equilibrium constant K is equal to CRE, equilibrium concentration of the product, divided by CAE, equilibrium concentration of the reactant, is equal to K1 by K2, and this would be equal to, so initially you had 0.05 into 2/3 divided by 0.05 into 1/3. So, this is equal to 2. So, therefore, K1 is equal to K twice K2. So, this is equation 2. So, now if we solve equation 1 and equation 2, we can get K1 and K2. So, solving equation 1 and equation 2, we obtain K2 is equal to 0.086625 by 3, which is equal to 0.028875 minute inverse, and K1 is equal to 0.05775 minute inverse. So, now we can write the red equation as minus RA mole per liter minute would be equal to 0.05775 minute inverse into Ca mole per liter minus K2, K2 is nothing but 0.028875 minute inverse into Cr mole per liter. So, this is the rate expression of the reversible first order reactions A2R, and this way we can solve the problem of the batch reactor data. Now, if we consider another example problem of variable volume system, the first order rate constant for the disappearance of A in the gas phase reaction, say twice A2R, and if on holding the pressure constant, the volume of the reactions mixture starting with 80% A decreases by 20% in 3 minutes. So, in this case, we can solve, say, initial volume of the reactor this is V naught, and then we can change the volume this is V is equal to 0.8 V naught, and the reaction is twice A2 product B. Amount of A or B, amount of A or B is, this is 0.8 and this is 0.4. From the stoichiometry, inert initially 0.2, so it will remain 0.2. So, total, if we consider total, we will get this is 1 and this is 0.6. So, from here epsilon A is 0.4. Since this is first order reactions, as we have derived for varying volume systems, we can write minus ln epsilon A plus 1 minus V by V naught by epsilon A is equal to kT. So, if we substitute the values, this would be minus ln minus 0.4 plus 1 minus 0.8 divided by minus 0.4. So, this would be equal to K into 3. So, from here we can calculate K is equal to ln 2 divided by 3, which is equal to 0.231 minute inverse. So, this way we can solve the varying volume batch reactor data using integral method of analysis for the first order systems. So, this is overall we have covered how to analyze the batch reactor data for constant volume and varying volume systems using both integral method of analysis and the differential method of analysis. Now, in the next lecture we will start with another module which will cover the reactor design for the chemical reactions. Thank you very much for attending this lecture.